Welcome to technology and direction fields. So again, note, as I mentioned in the last video, we usually use technology to create direction fields. Let me use something other than green. Sorry about that. So we usually use technology to generate direction fields. This way we don't have to run through hundreds of points or however many points to kind of figure out precisely the tangent line, right? So we don't need to spend a lot of minutes or a lot of time calculating all those individual slopes. There are quite a few programs out there. I'm going to be using one that's made available by Bluffton University. A professor has created this using JavaScript. You are welcome to use other direction field plotters. I've found this one to be pretty useful. So the website is listed here. There will also links from your homework assignments, as well as a link just from the end of the modules page to the direction field plotter. So following the link here, we have a direction field. I apologize, I completely forgot what equation we were working with. So here we are looking at p prime is equal to 0.05p times 1 minus 0.001p. This is a differential equation for a population model with limited resources. And then we're supposed to let x range from 0 to 200 and y from 0 to 1500. So we want 0.05p times 1 minus 0.001p. So if I go back, we have to do ours in terms of x and y. In this case, x is time and y is acting as our population. So we do 0.05y. Oops, that's not a 0. 0.05y times 1 minus 0.001y. So this is our equation. And you can see right now between x is -4 and 4 and y is -3 and 3, there's not much interesting going on. Let's go ahead and change our x from 0 to 200. And y from 0 to 1500. And you can now see your direction field here. So I'm going to take a picture of this and add it into our notes, and we can just kind of label what was going on. Oops. Now my screen's showing what I want it to show. Sorry about that. So again, here our direction field plotter only uses x and y, or sometimes you can use t and y, but it certainly does not use p. So in this case, our time is acting as our x and population is acting as our y. So we just rewrote the equation in terms of p and x as opposed to sorry, in terms of y and x instead of p and t. So I put in the equation, and then this was my 0 to 200 for the x coordinates and 0 to 1500 for my y coordinates. And then if you just click out of those boxes, then the direction field's set. So once you've had this, then you have to click outside of the entry boxes. And we get our direction field. And then the next thing we were asked to do is to plot solution curves. So we can kind of sketch solution curves easily if we want. So I can see that if I start sort of close to 0, that I'm going to go up and sort of stay at a fairly constant rate and then level off and seem to flatten out. If I start up high, say at 1500, I'm going to work my way down at a fairly steep rate and then level off. And presumably there's somewhere in the middle where we will go flat. So we can easily do this pretty much by hand, just adding them in, or we can use our technology. So I'm going to go ahead and switch over to the technology and again, draw the solution curves there. So to draw the solution curves, we can open the plot numerical solution curves. We're going to use Euler's method for now, which we will learn how to do sort of explicitly by hand later. But again, this is just sort of moving along using the direction fields. And then because we're going from 0 to 200, moving at 0.1 increments is very small. So let's go ahead and just move it increments of 1. And then for our first starting point, let's use, say, x coordinate of 0 and a y coordinate of 50, and then hit submit. And so we can see there a solution curve. If we start at 0, 0, if we have no animals to start with, we can see a green line just popped out. It stays flat. That makes sense. If you have no animals, how on earth would your population grow? If we started, say, with 500, and then see, again, it levels off at that same place. If we start with 1500, again, we have that steep drop and leveling out that we saw before. And then it looks like they're all leveling out right about 1000. So if we start instead of at 1500 at 1000, oops, sure enough, it appears we have a straight line. So this is a whole set of solution curves that we might work with. So once again, I'm going to take a picture and transfer this to our notes. So once again, just a reminder, what we put here for our H, this should be not too small in relation to the domain. So somewhere around sort of the width of the domain. So this should be from here to here, somewhere divided by, say, 200 minus 0 divided by somewhere between 100 down to that divided by up to maybe 500. So we could have done a variety of sizes, but the 0.1 that was in there originally would not have gotten curves that went fully across the board. It only does so many steps. So this is essentially how far it moves before it calculates a new slope. Here, this is our starting point. So we're starting at the 0.01,000 and then just hit submit. And then you can just enter as many as you want to get a variety of solution curves. So this is sort of what we can do to create a direction field. We're going to do one more. I apologize. Let me reset so I can find the instructions there. There we go. So for our next example, we're going to use the direction field plotter to create the direction field for y prime equals xy squared over y minus 1. So if we go back to our direction field plotter, we are working with xy squared. You need to put in a multiplication sign anytime you have two letters in a row, otherwise it gets confused. So xy and then caret squared divided by, and then in parentheses, y minus 1. Oops. Parentheses, y minus 1. And then if we create our direction field here, we wind up looking like this. So if I take this over to our notes, up top is what I entered. And then down below, we have our direction field that was produced. So we can kind of sketch what's happening again. Based off of this, we could sketch solution curves. This right here is already the direction field, but drawing some solution curves. If we start here, it looks like we fairly quickly get steep. And then if anything, we seem to kind of turn back around. Okay, so we might get things that are not functions from a direction field. If I start here, again, it looks like I turn back around. If we start here, it's a little hard to tell what's going on. It looks like we most likely flatten out and turn back around and work our way down. Same thing here. It looks like we flatten out and then work our way down. So we seem to have sort of flattening out and working down. It's a little perplexing what is going on. Sort of in the middle there, correct? So, but we know when x equals 0, we should be flat. When y equals 0, we should be flat, right? Since we are looking at x times y squared over y minus 1. So it looks like we may be doing something sort of like this. And then kind of mirroring on the opposite side. So we know when y equals 1, if we look at the original equation, when y equals 1, we'd be getting an undefined slope. So we're expecting infinite slope. That's what's giving us these sort of slight turnarounds back in the other direction. So we can kind of get a feel. This is obviously not perfect. It should be symmetric in sort of terms of x. So my solution on the right should probably go further out to match what was happening on the left. But you can kind of get a sense for what's going on, even if the direction field is very strange and we get graphs that are not functions.